Welcome back to Mathematics Lifeline. In today's video, we're going to be doing a work integral problem. So this is something you would probably see in Calc 2, and it has pretty good applications to engineering. And so I wanted to go through this one because it's a pretty interesting example. So it says you're in charge of the evacuation and repair of a storage tank that's filled with benzene, and benzene weighs 56 pounds per cubic foot. The storage tank is the upper half of the sphere generated by x squared plus y squared plus z squared equals 100. We want to find the work required to empty the tank if we pump the benzene to an outlet 2 feet above the top of the tank. So kind of a word salad here for this type of question. There's a lot of setup. But the important thing that we want to notice is that the tank is modeled by this equation for a sphere. So we're looking in the 3D plane essentially, and we have x squared plus y squared plus z squared equals 100. So what that is a sphere that has radius 10, and it's also centered at the origin. So instead of trying to draw the entire sphere, what we're going to look at is just one cross section of it. So let's kind of get rid of the z axis for a second, and let's just worry about x and y. So here's x and y, and we're going to try to draw just the upper half of a sphere. Right, so this is supposed to be the upper half of our sphere, and again, you can imagine an axis kind of pointing out at you, and this thing rotating around that, and that's going to be the entire storage tank. Okay, so and we also know that because it's equal to 100, that the radius is going to be 10. So it's going to be 10 there, it's going to be 10 up here. And the other thing that's important to know is that we're going to pump this benzene to an outlet 2 feet above the top of the tank. So let's get rid of the y for a second. And let's imagine a pump that comes out of here, and this height right here is 12. So this is 12 on our y-axis. So we're going to take liquid through this pump, and we're going to spit it out the top, and that's 12 feet above everything else. And we want to find the work that is required to do so. Okay, so this is a tricky question, and the problem is just the setup here. So let's go ahead and try to set up the integral that we need. So we know that if we're looking at this cross section, we need to integrate, right? Because we need to basically revolve this around the entire y-axis. So we're going to take the integral. Now we need to figure out our bounds. Well, let's think about what we're doing. We're pumping benzene that's all contained in this sphere. So the only thing we're worried about is how high up the benzene goes, and it goes from 0 to 10 on the y-axis, because our integral is going to be in terms of y. So the benzene fills all the way up from 0 to 10. Okay? Now, another thing that we're going to need for the work is to consider the density. But the density here is given to us because we know it's benzene, and the density is 56 pounds per cubic foot. So we're going to throw that in there because every essentially slice of benzene, if you think of it as kind of a slice right here that we're taking out, we're going to have 56 pounds per cubic foot. So it's going to weigh that much per cubic foot. So we need to throw that into the integral. And then what we also are going to need is we're going to think about the cross section vertically of this sphere. So like, again, this is supposed to be a sphere, so you can think of it as a 3D shape. But when we look at these cross sections, right, this little sliver I've taken out, this is going to be a circle if we look the whole way across here. If you're looking down at this, it'll be a circle. So when we look at how we can actually integrate that area, we need to use pi r squared, or the area of the circle, because we need to figure out how much each one of these slivers, how much area is involved. That way we can integrate around the entire y-axis. So we're going to use pi r squared. So we know we need pi, but what is the radius? Okay, well, the radius is going to actually depend on how high up we are on the y-axis. So again, we're going to treat z like it's 0 right now, but we know that x squared plus y squared now is going to equal 100, just because we're looking at this 2D representation of it. And we know that the radius is going to depend on y. So what we want to do is actually solve this for x, because if we solve it for x, then we'll have something that depends on y. So we're going to get x squared equals 100 minus y squared. And then to solve for x, we're just going to take the square root of both sides. So x is the square root of 100 minus y squared. But let's think about what we just found. We just found the radius, right? It's all dependent on where we are on this x-axis. So the x distance is going to be the radius of whatever cross-section we're at. Okay, so this is our radius right here, whatever x value is, which means this is going to be plugged in for our radius. So we have the square root of 100 minus y squared squared. So pi r squared, again, that's coming from the area of a circle, but we need to integrate that so that we can actually get the entire area that we have, the entire volume. I'm sorry. And then so now what we have is we have the weight essentially of each one of these slices that we take. So now that we have that, the only other thing that's going to matter for this work is how high are we actually lifting this benzene, right? It's coming from wherever we are here, pumping out, and it's going all the way up to 12. So the height is actually going to be 12 minus whatever the y value is, right? The height that it has to be lifted, because it's going to start from the top. So at the beginning, it's going to be 12 minus this really tall y value, so it doesn't have to go as far, essentially. But then when it comes down here, we're going to take 12 minus, if the benzene is now filled up to here, right, it has to go much farther. So it needs to be 12 minus, let's say, 1. So it goes up 11 units. So 12 minus y is the distance that the benzene has to travel through the pump. And that's actually it for the setup of the integral. So we'll put a dy here, and then now our goal is to actually evaluate this. So we'll get our answer in foot-pounds of work. So evaluating the integral isn't actually too bad. What we're going to do, I'm going to pull out the 56 pi, because that can come in later. Then we have the integral from 0 to 10. Now this squared, what we can really do is just get rid of the square root in the squared. So I'm going to do that really quick. Get rid of that. And then now what we need to do is distribute this out. Okay, so 100 times 12 is 1200. Then we're going to get a minus 100y. Then we're going to get a minus 12y squared. And we're going to get a plus y cubed dy. All right, and then now we're going to actually integrate now. So 56 pi multiplied by. Now if I integrate all these with respect to y, I'm going to get 1200y minus 50y squared minus, that's going to be 4y cubed, and then plus 1/4 y to the 4th. I'm evaluating this from 0 to 10. Okay? And then now when I evaluate, I'm going to get 56 pi times. If I plug in 10, I get 12,000 here, minus 50 times 100, which is going to be 5,000, minus 4 times 1,000, that's going to be 4,000, plus 1/4 times 10,000, which is going to be 2,500. And then when I plug in 0, I'm not going to get anything because all of those have a factor of y, so everything will go to 0. So now what this gives me is 56 pi times, this is going to be 7,000 minus 4,000 is 3,000, plus 2,500 is actually going to be 5,500. And then now for my final answer, I just need to distribute that out. And I believe 56 times 55 should give you 3,080, and then plus these two zeros. So this will be 308,000 times pi foot-pounds of work. And that is actually going to be our answer. So it takes 308,000 times pi foot-pounds of work. So it's going to be a little over 900,000 foot-pounds to be exact once we multiply by that pi. So yeah, this is an interesting word problem. It's tricky. You have to kind of know everything, and with it being pumped above the top of the tank, we have this extra height factor that comes into play. That's a little trickier than what it usually is because we do need the entire region or the entire height here of the pump. But yeah, I hope this was helpful. Again, I've seen this problem in tutoring. A lot of times people tend to get a little tricked by it. So if you have any questions, feel free to let me know. But if not, then I will see you in the next video. Thanks for watching.